Hi, everybody. It's very exciting for me to give a research update for World BBS Day, and I'm really honored to have been asked. I wish I could have been there in person. This is my team of researchers and collaborators. I don't have to tell all of you what Bardet-Biedl syndrome is. We're at least 29 genes and counting, and it's this complex syndrome of obesity, polydactyly, retinal degeneration, kidney failure, developmental issues in some people. Different people have different manifestations of Bardet-Biedl syndrome. But the vision loss is the part that I am involved with and that really affects people's lives significantly. At the University of Iowa, we have a Bardet-Biedl syndrome type 10 mouse model. And for those of you who can't see, I have pictures of the mice here. And the Bardet-Biedl syndrome type 10 mouse is very, very tiny when it's first born. We have to give it special food and take care of it in special ways. But as it gets older, it gets obesity, as people with Bardet-Biedl syndrome do. And it also gets retinal degeneration, just like people with Bardet-Biedl syndrome do. And we can watch this or monitor this on OCT, which shows us the layers of the retina, and on ERG, which shows us the electrical waveforms of the retina. And with generous research funding from Fighting Blindness Canada, the Bardet-Biedl Syndrome Family Association, and Envision 2020, we made a vector that would deliver the Bardet-Biedl syndrome type 10 gene. And this I'm showing a video of me doing a subretinal injection in a mouse that we do under the operating microscope, the same microscope I used for children, not in the same room, however. And you can see in the picture here, for those of you who are viewing, that the green area of the retina is the area that's treated. So with subretinal gene therapy, we don't treat the whole retina. We are treating whatever we can deliver with an injection that's given under the retina. In the mouse, it's about half the retina, and in humans, it's less than that, but we aim to treat sort of in the middle of the retina. And we made this visually guided swim assay for the mice. In humans, there's the multiluminance mobility test that was used in the Luxturna trial, where people navigate through sort of an obstacle course and different light levels. Mice don't easily navigate through obstacle courses, but if you put them in water and there's a platform, they will go for the platform and get out. And you can see in a mouse with normal vision, here I'm showing a mouse swimming to the platform. So we standardized this test using mice that had normal vision and then mice using mice that had no eyes at all to see how long it would take them to find a platform. And it goes without saying that the mice that have trouble seeing, it takes them longer to find the platform, but they do find it eventually. Just like people who don't have good vision, they get techniques, they learn how to find the platform. But with a treated Bardet-Biedl syndrome mouse, they really can find the platform as quickly as a normally sighted mouse. So that we knew that the treatment was working. And this is a graph that shows that it was statistically significant. And the most significant thing that we found was, I'm showing electroretinogram tracings, and this is showing the electrical activity of the eye. And in a treated mouse eye with Bardet-Biedl syndrome, there's our two little spikes of electrical activity. And in an untreated eye next to it, there is a sort of a wiggly but flat line. There's no electrical activity measured. And so all of the mice from the earliest age with Bardet-Biedl syndrome have no recordable electrical activity from their cones. But once we treat them, they actually get to normal cone activity on the electroretinogram. It kind of decreases a bit over time, but they have a very good response to this. So we're very hopeful about this when it comes to humans. So it works in the Bardet-Biedl syndrome type 10 mouse. So how do we get it to people? Well, we had to make a new version of the vector that had the actual human gene in it, because to treat the mouse, we put the mouse gene in. It's very similar to the human gene, but it's not exact. And then we had to repeat the testing in the mouse to make sure it was still safe. And then we could either try to start a clinical trial from scratch through the FDA, or we could work with a company to try to get it to patients quicker. And what we chose was to work with a company. And the company is Mira GTX. And we got more funding from Envision 2020. And I do want to just say that the Bardet-Biedl Syndrome Family Association in the US gave us sort of emergency funds during COVID to keep these mice alive because we had already injected them and they were kind of asking people to decrease the number of mice they had and stuff. So I just want you all to know that patient advocacy played a huge role in this research. But when we got to this collaboration with Mira GTX, we tried two different promoters. That this is what kind of regulates where the gene will get expressed. And one of them was just in the photoreceptors, the cells in the retina that die first in Bardet-Biedl syndrome type 10. And the other was a CAG vector promoter that makes the gene express in all the cells of the retina. And we actually found that that CAG promoter was toxic at high doses, whereas the RK promoter, which is just in the photoreceptors, was well tolerated at every dose. So that was safer. So we moved forward with that one. We tried multiple different doses. And we did this in 1-month-old mice that are maybe equivalent to 3 to 4-year-old humans as far as the retina goes. There's not a direct correlation, but that's kind of what we think. And we found that in these mice, even out to 5 months after treatment, which is pretty long in a mouse, that we could record that electrical activity, especially in the high dose group, but also in the low and medium dose group. And that was for the rods, the cells that see in peripheral vision and see in the dark. And then the cones also had a really robust response, especially to the highest dose group. And really excitingly, when we looked out 16 months after treatment, which is really the end of life for a mouse, we did a cone stain on the retina of these mice. And what I'm showing here is an image of, it looks kind of like an X, but that's the eye, the whole eye that we've kind of cut so that we can lay it flat. And the green areas there are cones. They're staining with a cone stain. And the one on the left has bright green all over the place. It has a lot of cones. The one on the right has no cones whatsoever. And the one on the left is from a Bardet-Biedl syndrome type 10 knockout mouse. And so is the one on the right. They're the two eyes of the same mouse, but the eye that got treated kept cone function or cones all the way to the end of life. And when we did the swim assay, we saw that they did keep cone function as well. So we have a lot of different markers that show that in the mice, this really, really works to improve and delay loss of vision. So what have we learned? Well, we can activate these dormant cones and delay retinal degeneration in very young mice. We also tried this. Brianna Schoenfeld was a student in our lab who did this with older mice. And the older mice didn't have as much cone function recovery, but they still had improvement in vision on that swim assay. And also they kept their rods much longer. So even in older mice, which would we hope correlate to older people, there's some rescue of the retina. And so in collaboration with Mira GTX, this GMP grade vector was made by Mira GTX. We also did a natural history study at the University of Iowa, and I thank all of the patients who participated in that because that helps us know what endpoints to use for the human clinical trials. So we really appreciate that participation, and we're going to publish that data very soon. And finally, the most important thing is that the first patient has been dosed with this vector, and we hope to have more news on that in the very near future. Thank you.